Hi, my name is Sandoval. I'm a faculty and an extension specialist at UC Davis, and today we're going to be talking about water resources modeling. So for today, this is what we're going to be talking about. First, a little bit of water resources modeling, and then simulation modeling. Um, this is one of the field trips that we used to do at the class. So anyway, you used to see this water resources system from the top of the hill. Now I'm going to explain you in some pictures. So let's take a look at some water resources systems. As we have seen, California has a very complicated water resource system. Think about this. So all the different, so in terms of natural availability, see how all the different rivers throughout the state and the different amount of climate and change in climate that we have throughout the state. And that is the natural variability that we have. Now, think about all the different reservoirs that we have in here. And associated with, so the reservoirs is a way to park the water, to have these time machines that will move water in a space, but also think about all the different users. So users throughout the Central Valley, throughout the different valleys in the state. So reservoirs are operated to supply some of their water needs. Also think about the different cities. So for instance, here in the city of Davis, I mean, some of that water comes from the Sacramento River, which basically is regulated by many different reservoirs. So for instance, Shasta, in the Feather, from Oroville, New Bullards Part, and so on. So we have all these different water users, well, natural availability throughout the state, then water users, cities, farmers, the environment, and so on, and then the different infrastructure. So you can see we have a very complicated water resources system. Now, this was only in terms of surface water. If you think about groundwater, this is what we have for the state. A lot of the water that is coming from, it can be the rainfall or snowfall, and then it will go throughout the rivers that are recharging aquifers, different either treatment plants that are putting water back into the stream, or that they can put it back into the aquifer, and so on. So as you can see, we have all these different pieces, how we're using water, the different infrastructure, the order of who is using water at what a given time, when, and how much. And as you can see, in order to organize all of this, well, there is a need for tools. And in this case, a need for tools to be able to see, well, to distribute, to organize how we're distributing water here in the state. So this will be, again, so we're going to be talking in this class and the next one about simulation and optimization models. In this case, simulation models predict a response to a given design. So what does that mean? That given that you have certain natural inputs, so you have the water resources system. You have some of the natural water availability. It can be in terms of groundwater, surface water, snow, rain, fog, and so on. Then you have a water resources system, that those were the previous pictures that I showed you. And then you start defining certain system and operating policies, so certain policies on how people are going to use water and how the infrastructure will be used. And then you get some system outputs. Then you get a certain response, certain results that later we analyze, as you have done it in some of your exercises. Optimization is a different one. Optimization is not this linear interaction. So basically, as you have some inputs and the resource system and certain constraints, you will try to find what will be some improved, optimized operation policy or system design. So it is a different one. But for now, we're going to be talking about simulation models, which again are those that predict response to a given design. And we're going to be talking about it. Optimization models, they identify optimal design or operation, and this is what I was talking, an improved way to actually operate the system. So let's think about this. So simulation, to be more specific, it addresses the what if question. What do I mean to what if? So basically, what will happen if we have a water demand in the river? What will happen if we have a given order of priorities between user 1, 2, and 3? What will happen if we build a reservoir or if we don't? So it responded those what if questions. And when you get the results, then what likely will happen? Again, remember that models are good approximations. They are not the entire reality. They are good approximations. They include large hydrologic, economic, and environmental data. So you can put a lot of not only one inflows, but you can have a fully description of the hydrology, the hydrologic cycle, some of the economic benefits for different water users, and some of the environmental data in terms of weather, in terms of climate, in terms of response of different aquatic and riparian ecosystems, all the different rainfall and land surface processes, and so on. So simulation are very well known because they evaluate a change given they evaluate a system given a change in a policy or in a design. What does that mean? That you describe the system and then you say, well, this is like if you were in a wet lab. You have an experiment and then you say, well, what if instead of putting this, so to that specific experiment, what if I change the reaction or the component of this and that or that? It is the same. So you have a system that is already represented or described, and then you start changing, what if I build a reservoir or if not? So you just kind of change that variable. What if I change the priority in here and there? So that's what you're seeing, and it is kind of like you being on a bench, on a wet lab bench. Usually what happens is the following. So this will be the process for a model to kind of work or run. You start the model, you start the calculations, and at that time you have certain initial conditions. Typically it's an initial storage. You need to initialize your model in order for it to run. And those are also sometimes boundary conditions. Then you step into the first time step of the model, and then you read the inflows. You read, in this case, you have seen how much water is coming from the river upstream. Typically that will come in a file or so. Then you compute some of what will be the allocation of the different parts of the river. Then you will compute how much water will be left to the river, released from the reservoir, and so on. You store that data. You calculate, in this case, what is the next time step of the storage, so how much water will be left in the storage. And then at that point, the model thinks like, am I done? Have I finished the number of time steps that I have to do? And if not, then it will go back at another +1 to the time step, so that will be time step number 2, reads, calculates, estimates the change of the storage, am I done? And then go back. Otherwise, it will just end it up. So you can see that it is cyclical. Something that I explained before is that this starts with knowing something from the previous time step, calculating time step, and that specific time step, and then when you move to the next one, get some data from the previous one. That's what it is, this concatenated calculation. So let's think about a water resources system. And again, we have seen this in your exercise. So you have 3 users. Each user has a given priority, and it has a reservoir and some water coming in, okay? So that will be a water resources system, and we are describing it, okay? We want to build a simulation model. So the bare bones of a simulation model, how you can think of that conceptually, is that you're going to have certain inputs. You're going to put certain policies. This simulation model describes this water resources system. So the inputs and the policies, also with the topology, so what is the different locations, the different, the location of the different users and the different infrastructure, that will be, once you have those two things, the simulation model will go time step by time step and try to fill it, and then it is going to get some outputs. This is the basic concepts of how to build a simulation model. You have some hydrologic inputs, some policies that you want to describe. You describe the water resources system using these two and the specific geography of the users, and then you get some outputs. Now, in this case, as we have seen, we have some hydrologic time series, some inflow data. And that one is related to, in this case, to inflows. So we have had that time series of inflows, and that will be our input data. And as you have seen in the exercise that you have been working on, so those hasn't changed. So we have exactly the same inflows in part 2 of the river, and also the same ones that we have here in the reservoir section. Now, when we're talking about policies, what do we mean about policies? So the first one is this allocation. And this basically defines who gets water first and what type of demand. And so basically that graph that you're seeing there is a graphical description of this, of who is taking water first, second, and third, and which is basically the river taking water first, then user 3 taking water second, and user 1 and 2 taking water third. And that will be depending on the water that will be on the river. In this case, well, that will be for this case, for water will be on the river, and in this case will be the water that is stored in the river plus the water coming in. So this graph, it basically, it represents that specific demand that is coming from, or that water allocation system coming from this specific range. So as inflows, this reservoir storage plus inflows are changing, then you have different water allocation to different water users. Okay, so that is one policy, and I do want to remember that that's how we're declaring a policy in this simulation model. The next one will be this: if we have infrastructure, then out of this policy and the infrastructure will come a reservoir operation policy. And this one, basically what it says is that given that I have certain amount of water plus water coming in or plus inflows, this will be the amount of water that I'm going to release. So the release, it depends on this allocation policy. This allocation is telling who is going to receive water, and then adding all of this, it will develop you this reservoir release policy. That's what we have in here. This is what we're talking about policies. And again, so we went from this kind of very simplistic to now know that we need some hydrologic time series inputs, some allocations that will be part of the policies, then the infrastructure and the policies for operating that specific infrastructure. And once we have done that, then we have certain model outputs. And this is some of the things for user 1, for user 2, for the river in what will be the allocation for the river. So that's pretty much a water resources simulation system. As we have seen, so now at this point we're going to be talking about the reservoir and operating policy. In this case, we have described this specifically for the reservoir. What we have is that the reservoir, it has this kind of shape. So the water released from the reservoir will be equal to the demand, or it will have this kind of linear release. But once you have water stored in the reservoir that is the same amount of the demand, then it will only release the demand. And that's basically what you have seen here in your exercise. So when the reservoir plus the water coming in, the inflows are about 12.5 units. At that moment, after that, so when you have that water stored in the reservoir and water coming in about that much or greater, it will only release the demand. Otherwise, it will release the amount that we know as is associated for each of the different water users. And that's why you see that also these lines now are flat, because it's releasing only this water demand for each of them. Now, the other case will be, and in this case, the release of the demand, and the demand will be met. Here will be some deficits. When water is being released in this area, someone is going to get a water supply deficit. It will not be fully meet their demand. Then we can go to the opposite side of the operation, where it will be when the reservoir is very full. And basically in that one, when the reservoir is very full, so if the that water in the, so the water is stored at the beginning of the time step plus the water coming in on that step is greater than the size of the reservoir plus all the demands downstream. So if that is the case, then that excess of water will be spilled, and it will be in this amount. So that will be the excess of water from this minus this amount of water, which is basically this release of the water demand, and then the difference between this line, if we have projected in here, plus this distance, that will be the spills. Okay? Hedging rules, and basically this is this specific demand that it is a one-to-one slope. So you get 1 unit of storage, you release that unit to meet a water demand. You can actually have it a little bit more tilted, more inclined. And in that one, basically what you can say is that, well, I'm not going to release that one-to-one unit. I will release 0.8 units of water and try to save some water in the reservoir. So if we have a prolonged drought, I will be able to supply more water for the different water users. And that will be pretty much this part that in your exercise for extra points I put it in here, which is basically this will be that one-to-one relationship if you put here 0.8. As you can see, this one will go from that one-to-one slope to now 0.8 slope. And what it will do is actually it will change the water allocation for different water users. So this used to have this water supply. You do this 0.8, then it will have a less, it will have a lower water supply. Why? Because once you are in this portion of the storage, you're not releasing a one-to-one relationship. You're releasing less water because you know that there is going to be a shortfall and you do not know what is coming the next year. So that's what this hedging rule is about. Last but not least, we have something in here that is the performance evaluation. And in this case, think about that you have a given water demand. So this is the water demand that you want to meet for a specific water user. And you have 10 years that you want to supply that water demand. The green portion is what you have actually supplied, and the difference between the green bar, what you supplied, compared to that water demand, that in this case is fixed, is a water deficit, a water supply deficit. It's the amount of water that you were not able to supply. So in this case, that will be that amount. So you have 2 years with 100% water supply compared to the demand, and then you have some years that there was a drought here, you were not able to make it all the way to the demand, and then this year you'll come back. So in terms of time, it will be the number of times that you meet completely the water demand. That will be the time-based reliability. This is one of the performance criteria. This is how you can evaluate the performance of a given policy. And again, you have these policies infrastructure, you change a policy, and now you want to see how is it compared. What is the performance of that policy? In this case, in terms of time-based reliability, it will be this number of times that it was supplied fully, which is 6 out of the 10 time steps. So 6 over 10, it will be a water supply reliability of 60% of time. 60% of time you were able to meet this water demand. In these terms, in terms of the reliability of volume, you sum all the water supplied, so all the green bars, compared to what will be the water demand times 10. So the full water demand that it was requested compared to the water supply. And in this case, I don't know, I mean, think that it might be 70% or 80%. So of 80, if it was 80%, it will be of all the water demand requested, 80% of volume was able to meet. Some years 100%, some years less than 100%. But it gives you an idea of how much water was totally supplied. So reliability in time, 60%, reliability in volume, perhaps 80% here. Then we have this vulnerability. And vulnerability looks to the glass empty. In this case, it will be to what is the average of the deficit. So you have these deficits divided over 4, it might be, let's say, 20%. So 20%, it was the 20% compared to the demand. When you have a deficit, the average of that deficit, so you add these 4 green bars over 4, that average is 20% compared to the demand. So now you have an idea, 60% of the time I supply water. Overall, I provide 80% of the volume. When I have a deficit, when I cannot meet that demand, on average, it will be 20% of that demand. Then the next one will be how fast can I recover? And in this case, it will be, if I have a deficit, does the following year, do I recover? Do I supply 100% of that demand? So in this case, it only happened 1 out of 4 times. So until this 4th time, it was able to recover the system, given that you have 4 chances to actually recover from a deficit. So in this case, 1 out of 4, it will be 25%. Again, we have 60% reliability, 60% of the time I was able to meet the demand, 80% of the volume, I was able to supply 80% of the volume. Vulnerability was 20%. The average of the deficit is 20%. When I failed by on average 20%. And I have a chance of recover of 25%. If I get in a deficit, usually I'm there 4 years before I can recover. Now, a lot of this is quite a lot. And you can actually think of this in how to synthesize this performance. And basically, that's why you develop an index. An index is a way to put all these results into one number. And then rather than going through all of these, through all these different water users, throughout all the different basins, now you synthesize it. And in this case, something that we propose is a water resources sustainability index, which is basically the geometric average. So you multiply all of this. You multiply the reliability of time for a given user I times their volumetric reliability times the resilience, and 1 minus the vulnerability. 1 minus 1, because basically these are, there is a good performance when these tend to 100. Vulnerability is a good performance when it tends to 0, when it's closer to 0. You really want to have a system that is no vulnerable or small vulnerable, but you want to have a very high reliable system, a very high resilient system. That's why it is 1 minus the vulnerability. And because it is a geometric average, you multiply everything. Basically, if there is one that is not fully met, each of these are kind of essential. You want to have these very well met. If you have an arithmetic average, so if you add all of them and divide it over 4, even though you have one bad performance, because you may have 3 good performance, the overall index will be pretty good. It will be good. Multiplying them, you added a weight to the lower performance. So you actually kind of make sure that all of them are kind of improving at the same time. So going back to that, we have seen in our exercise in this part 1 that when you have a system with no reservoir, and you have estimated, so this will be the system with no reservoir, and again here you're seeing all the different results, but when you go back here, you can actually say like, well, you know, actually these are good results for this. You can see that in the case for the river, I have a 95% reliability in time and in volume. I have 100% resilience, but when it fails really hard. I actually cannot provide water to this user. That's why it has a sustainability of 0, because basically when you multiply all of this and 1 minus this, it will, one of these, actually 1 minus this, it will be 0. This is in percentile, think of it as a fraction. And that's basically what is going on here, that you have very good performance in all of them, but excepting one, and that one is what it gives you a 0 reliability, 0 sustainability index here. Now, here will be the same. You have this very good reliability in time, volume, good resilience, good vulnerability. You have this good performance or better performance compared to the other users. And this because we know how they have the same priority and so on. They have the same sustainability index. And this will be a way to synthesize all these different water supply performances. Now this will be without a reservoir. When you compare this with the performance with a reservoir, then you can actually start seeing some differences in here. So now in this case, what you can see is that this one went from 0%, so this will be with no reservoir, and this will be with a reservoir. So the river went from a 0% sustainability index to now 100%. And so on the same. So user one, it has an improvement, just a tiny bit. These other ones receive an increased improvement. So overall, I mean, it seems that the reservoir is doing pretty well. I mean, later we're going to be seeing how reservoirs affect the environment, so don't take this as the whole truth. But this is an example to see how we can synthesize data and make it easier for us to understand. So going back to this, rather than having all these different things, now we have results for a given. In this case, this was for the reservoir operation policy. These results. So that's how you can kind of wrap it up this water resources system simulation. Hey, thanks for joining. I hope you have enjoyed the lecture, and I'll see you around.